So welcome back. Now we are having our 14th session, which is also the second session. So in this session, we have papers on perception, on control, and on planning. And our second speaker will be Daniel Rakita, and he will tell us a story about the remote telemanipulation with adapting viewpoints in visually complex environment. Please enjoy.
In this work, we introduce a method to support remote telemanipulations in complex environments by providing operators with an enhanced view of the task environment. To motivate this, suppose you are remotely controlling this robot arm in this kitchen environment, and this is the view provided to you by a camera in real time. In this case, the viewpoint happens to be sufficient for picking up this object. But what about if your view becomes occluded, such as by items in the workspace, or by the robot itself? Or what if you need a very particular view in order to successfully complete the task, such as viewing this toaster from above in order to place the bread? Lastly, what if you want to check if there's a mixing bowl you need on the counter just outside of your field of view? In our work, our central premise is that the camera should dynamically move in order to continuously adapt and improve the viewpoint to better support effective manipulations by the operator. Using this approach, the viewpoint can adapt to the geometry in the environment in order to see around occlusions caused by items in the workspace or by the robot itself. The viewpoint is able to adapt to the semantics of the task to provide a specific view given the task at hand. And the operator is able to independently move the viewpoint to visually explore the environment, get their bearings, and plan future actions. In order to move the camera on the fly, our method uses a two-robot system where the user controls a manipulation robot and a second camera-in-hand robot alongside the manipulation robot continuously servos to provide a sufficient view of the remote environment. In this example, the second camera-in-hand robot continuously servos to adapt and improve the viewpoint to see into the drawer, and the user is able to reach into the drawer in the remote environment using the provided view on screen. The user is able to naturally control the translations and rotations of the manipulation robot's end effector using a motion controller in their dominant hand. And they are able to visually explore the environment and provide suggestions for how the camera should move given a motion controller in their offhand. We utilize the RelaxIK solver to achieve real-time motion optimization performance in our method. The solver uses a flexible nonlinear optimization formulation to account for motion synthesis problems that dynamically trade off between multiple objectives on the fly, and is able to achieve per update motions that accurately match end effector pose goals without exhibiting collisions, kinematic singularities, and joint space discontinuities. We incorporate our geometric, semantic, and visual exploration viewpoint adaptation types into the RelaxIK optimization formulation by adding additional terms in our objective function. We have evaluated our method using two evaluations, including a user study, where even novice users were able to control the robot to complete various tasks in complex environments. Such tasks included a sock sorting task, getting kitchen items off of shelves, and organizing pills in a pill tray. For details on our results, please read our paper or come talk to me at the poster session. And there's more. Our method generalizes to any two robot arms, and we provide open source code to set this up. So thanks so much, and I'll answer any more questions after the session or at the poster session. Thanks.
Well, our third paper will be Trajectory Optimization on Manifolds, a theoretically guaranteed embedded sequential convex programming approach. The presenter will be Riccardo Bonelli. I'll give time to you.
So, good afternoon. In this paper, we provide a fast algorithm for solving trajectory optimization problem in the presence of manifold type constraints. The key tool that we leverage is the notion of geometric embedding. So recently, many trajectory optimization algorithms have been designed, but they have been tailored to work for Euclidean setting. However, naturally, robotic systems evolve on manifold. An example you have in the picture where a manipulator can be mapped to the torus. Our idea is to leverage geometric embedding to lift the original problem into a Euclidean setting and apply state-of-the-art sequential convex programming algorithm to solve the original problem. So let's take a closer look to the formulation. We try to solve this optimal control problem for which we minimize the following cost. The function G represent non-manifold type constraints such as collision avoidance constraint. We are in the presence of control-affine nonlinear dynamics, and of course the presence of manifold type constraint is given by this n-dimensional manifold M. We leverage a class of embedding theorem known as Whitney embedding theorems, thanks to which we can identify the manifold M to a closed submanifold of an Euclidean space. This allows us to define the following embedded optimal control problem for which we extended all the considered mappings to an Euclidean space. The key result is noting that trajectory is a solution for this problem if and only if it is a solution of the original formulation. At this point, we can adopt standard sequential convex programming techniques in Euclidean space, for which we design a sequence of convex problems that we call linearized embedded optimal control problems, in which we linearize every nonlinear terms, both in the cost and in the dynamics. And as of common use, we add some trust region type constraint to robustify the whole procedure. All these steps can be summarized in the following algorithm called embedded sequential convex programming. Our main theoretical result states that ESCP converges to a local geometric optimum of the original problem. That is, it finds a point that satisfies original manifold type constraints and, moreover, condition of optimality in a general strong geometric sense. We apply such framework to several robotic systems, showing that we run faster than common state-of-the-art algorithms such as TrajOpt. The deep analysis, theoretical analysis we provided gave us some key insight to further accelerate this procedure. Indeed, we were able to exploit a convergence of related Lagrange multiplier to define, leverage indirect shooting method to accelerate even find time faster, this kind of method. For further details and development, please spend some time at our poster section. Thank you very much.
Now we are having our fourth talk, and the title is Toward Asymptotically Optimal Inspection Planning via Efficient Near Optimal Graph Search. And the first author, Mengyu Fu, will tell us more details. Yeah.
Hi everyone, I'm Mengyu from UNC Chapel Hill. I'm very glad to represent our work on inspection planning. So in the case of inspection planning, we have a robot equipped with a sensor, and we are to inspect a set of points of interest in the environment. Inspection planning has many applications, from using unmanned aerial vehicle to do structural inspection of a bridge, to using an underwater vehicle to inspect a ship hull, all the way to using a medical robot to do endoscopic tasks to do inspection of human anatomy. Let's take the medical case as an example of inspection planning. Pleural effusion is a serious medical condition that could cause the collapse of the lung. To accurately diagnose the cause, doctor needs to visually inspect the inner surface of pleural cavity. Here, the robot we have is the CRIS robot, composed of a camera tube and a snare tube. Our sensor is a chip-tip camera, and the points of interest are the points lying on the inner surface of pleural cavity. Then why is inspection planning hard? First, to inspect these complex structures, the robot has to move in a geometrically complicated environment. And optimality in inspection planning considers inspection and efficiency. Primarily, we want to inspect as many points as we can while considering sensor constraints. And we also need to consider plan length, which could correspond to procedure time or distance traveled by the robot. For example, we need to consider battery constraint for mobile robot. It is even more important in a medical case because the procedure should be completed as fast as safely possible to reduce costs and improve patient outcomes, especially when the patient is under anesthesia. So here we present a novel algorithm, ARIS, which stands for Incremental Random Inspection Roadmap Search. ARIS reasons about inspection coverage and plan length simultaneously, and it also provides asymptotic optimality. In ARIS framework, we iteratively densify a roadmap and do graph inspection search, which computes the optimal inspection plan on the roadmap. Unfortunately, this optimal search is already computationally hard, so the key insight is to do near optimal graph search instead. Here we introduce two approximation parameters. Epsilon defines a relative upper bound for the plan length, and P defines a relative lower bound for the size of inspection coverage. We believe this algorithm is the main algorithm contribution that could have applications beyond inspection planning. We do parameter update between iterations to guarantee asymptotic optimality. We present results for the CRIS robot shown here. Inspection planning for the CRIS robot is hard, not only because the nature of inspection planning, but also because the kinematic computation of this robot is expensive. In the simulation scenario, the CRIS robot inspects points representing the surface of pleural effusion, which is the space between lung and rib cage of a patient whose lung has collapsed. We need to maximize inspection coverage to ensure accurate diagnosis and also to try to reduce procedure time. We compare our result with a state-of-the-art method randomly exploring random tree of trees, in short, RTOT. We first look at computed time versus inspection coverage. Here we have a logarithmic time axis. For the time given, ARIS produce more than 10% better coverage than RTOT. And to get the same coverage, ARIS is more than 25 times faster than RTOT. On the other hand, ARIS produce plans with similar length as RTOT. Thank you for your attention.
Now it's our last paper in this session. It's a semi-autonomous robot teleoperation with obstacle avoidance via model predictive control. And our speaker will be Elmas Shintamira-Rox.
My name is Almas Shintamirov. I represent Nazarbayev University from Kazakhstan, and we worked on robot teleoperation using non-linear model predictive control and with optical avoidance. Basically, our work initiated by our initial research on real-time robot manipulator control with closed-loop control architecture, so that we just can impose only joint velocity and position trajectories to the robot. And at the same time, we worked on inertial motion capture system design, and we decided to merge it for semi-autonomous teleoperation control strategy design. So we can provide only end effector trajectories to the robot manipulator, and the robot does the adaptive motion in the process, avoiding obstacles. We decided to use model predictive control to provide a human motion, not only the end effector, the current end effector pose, or the reference pose, and only also a forecast for the human arm motion, so that the robot generates the trajectory, take into account the trajectories of the future motion of the arm. of the operator arm. This is our initial design of our human arm motion tracking system. We use two IMU models, sensor modules and a potentiometer sensor module for joint, for the elbow joint angle measurements, so we can track 7 degrees of freedom of the human arm motion with respect to the shoulder joint. We formulate our arm motion using the quaternion algebra, so as orientation and position, and the optimization problem we defined as the difference minimizing the error between the human arm motion and the hand motion and the robot end effector position and orientation, and also we minimize joint velocities to generate the smooth real-time robot motion. We define 2 types of obstacles. Type 1 obstacle, we represent half space constraints like floors and walls. And type 2 obstacles, we use convex shapes to define objects on the way of blocking the direct robot motion. And at the same time, we also model the robot frame itself, covered with the convex shapes like spheres, so that the optimization problem solves the problem, basically generates the trajectory while comparing the convex shapes represent the obstacle and represented the robot frame, so that basically the trajectory avoids the collision between these convex shapes. These are the video demonstrations of our work. So the task in this case to bring the bottle object to other side of the scene, and the robot in the process, while teleoperating by the operator, does this automatic generation of the obstacle avoidance motion. So it was not directly imposed by the human operator, and the robot itself basically generates that motion. In this case, we assume that the object, the obstacle, the computer cases, the obstacle is known to the system. In the second experiment, we just defined the threshold limit 10 centimeters above the table level, so that even if the reference from the human operator goes beyond that the table level, so the robot does not collide with the surface of the table. So that in this case, we just basically, the robot satisfies the constraint of that. And the third experiment just demonstrates the stability of the system, so that the robot just perfectly tracks the human hand position. Thank you very much.
So all speakers, please come on and line up on stage. So now we have roughly 10 minutes for the question as before. Yep. Come on. The first question. There, okay.
This is for Daniel Rakita. Great talk. Do you have a formal theory of viewpoints for determining what is the right viewpoint for a particular task?
That's a great question. Thanks for that. So we first inspired how viewpoints should adjust in our work by looking at how people actually adjust their viewpoint. So we looked at the Epic Kitchens data set, which is like hundreds of hours of first-person, GoPro view of people just doing tasks in their kitchens. So we had someone go through and code that data, and that's how we were inspired by how our optimization should work. So in terms of a formal kind of framework for doing this, I think it's still an ongoing thing, but at least we wanted to frame this in terms of at least how people do it, since in this case, that's how, we had a human in the loop controlling the robot. So we wanted to at least frame it on that kind of inspiration.
Any other question?
Yes, I have a question for the second speaker as well.
Please raise up your hand because we cannot see you. Yeah. Okay, there.
Yes. So how does human control the robot to grasp something? Because I could imagine if there's latency for the manipulation setup, it will be extremely difficult for a human to grasp something.
For sure. So grasping in our system was very simple. It's just a trigger on the Vive motion controller. It's just a toggle on and off. Using the Robotique gripper, it has enough kind of compliance to account for a lot of objects that way. You can imagine, extending that grasping model to something more advanced and more general for more kind of grippers, but that's how we were doing it. But in terms of the motion to actually get to the object, I definitely agree that latency could become an issue, especially at great distance. Usually, we refer to like the remote surgery literature, and they say, if you're below the threshold of about 1/4 of a second, it's the resulting performance is not going to degrade so much. So that's kind of our bar. Like if we're below that, we think we're good. But I definitely agree that that's an important thing to keep looking at in this line of work.
Any other questions for our other speakers, please?
Hi. Yeah, I think this applies for both the second and the fifth speaker. In both of your projects, you have this thing where there's an automatic system that kind of distorts your control viewpoint, right? It's like suddenly the camera moves, so your hand is here, and then it feels like your hand is somewhere else. Or suddenly the robot arm is stuck and your hand keeps on moving, so like right, like you know what I mean? Have you thought about ways to make it like sort of feel less awkward when the system intervenes and suddenly changes your viewpoint?
So maybe our fifth speaker can give us some comments.
Thank you for the question. Our initial goal for this work was just the design a stable, like the control, in which we teleoperate the robot in real time. This the problem that you pointed is very important, and we didn't actually work on that at the moment, but basically we feel that there is a problem in this, and we are working on that now. I don't have current the answer for that at the moment, but hopefully we'll have some.
Yeah.
Right. If you can give us some quick kind of maybe comments or something like that.
Yeah.
Right.
Yeah. So that's a great question. So just applying this briefly to the viewpoint thing that you brought up. Actually, in prior work, we looked at how the control frame should actually update given the dynamic camera view. So the control frame is always relative to how you're looking at things on screen, and that we found created a huge performance difference compared to just like an absolute frame. But yeah, I agree. Looking at how to make these things more natural without fighting against this autonomy is definitely the way to think about it.
Thanks. Any other questions, please?
Here, one question.
Please, raise up your hand, because otherwise we cannot see you. Right.
It's a question for the third speaker. After you lift your problem, what was the motivation to use sequential convex programming and not any other NLP method with higher convergence rates? Thanks.
Yes, so thank you for the question. Basically, we try to use method for which we can ensure theoretical guarantees of convergence. So the idea was like to as you mentioned, this lifting can, then once you lift, then you can apply whatever algorithm you want, basically. And the idea is we try to apply SCP because we have already developed like a theoretically founded SCP framework named Gusto in our previous publication that have very strong theoretical guarantees, and we wanted to leverage that theoretical guarantees even in the presence of manifold, especially for this acceleration procedure that use this information retrieved by Lagrange multiplier to initialize correctly indirect shooting methods that are methods based on Newton methods so that they converge in very few milliseconds. So we really gain in speed, like we achieve 5 or 6 times faster convergences. So.
Any other question? So I have a question for the fourth speaker, Mengyu. So you analyze or you give some kind of a guarantee or some theoretical bound on your planner, right? And you mentioned something like the P dominance or something. So how if you compare between your method and the other kind of related work based on the Pareto optimization, if you know that?
Thank you for the question. very good question. So, so the important thing in inspection planning is that we consider efficiency and inspection at the same time. So we cannot only look at one criteria. So we need to deal with these two criteria at the same time. So there is actually a balance between efficiency and coverage, because if you want to inspect more points, you might want to go longer, and if you want to save time, you cannot inspect too many points. So, but we deal this problem as we first want to coverage as much point as we can, and also save time. So these two things are simultaneously considered in our framework. So I think it's something different from if other Orbital algorithm that considers only one criteria.
All right, good. I have the last final quick question for William. So, right, so in that way, then, so is there any comment or some hurdle that you can comment, kind of extending from your visual odometry to the SLAM?
So the main hurdle we have currently is our thing only produces a local maximum, not necessarily a global maximum. So if the pictures are too far apart, it gives nonsense answers. So you have to be reasonably close to begin with.
Okay, good. All right, so let's thank our speakers again. And, all right.